Now it works. So, I'm Ola Kristensson, I'm at the Department of Engineering, Cambridge, and what I talk about here is actually some of my own research, which spans both mobile interaction and clever things you can do with machine learning when designing new user interfaces. So I'll start by talking about my own research trajectory. Let's just give a brief overview where I come from. So I've done a lot of work in text entry interfaces, gesture-based and speech-based interfaces in particular. For instance, the gesture keyword, a little bit about that in a few minutes. Touch point correction for keyboards, multimodal speech, mobile speech, and touchscreen interfaces, and optimized thumb keyboards, etc. Pressure-based keyboards, you get the point. I've also have another strand of research in augmentative and alternative communication, which will not be in the workshop. And it's basically about enabling individuals with motor disabilities, non-speaking individuals with motor disabilities, to quickly communicate with other users via speech synthesis. So we've done some work here on using crowdsourcing and statistical methods to build very good statistical language models, but improve the prediction of these systems, which in the end increase the throughput of the system and helps people, disabled users, speak more at a faster rate compared to their speaking partner. And we also has taken that system and converted that into a phoneme-based system for illiterate disabled users. So this system allows people to sound out words and learn how to write essentially using phonemes instead of letters. And finally, we've done some work on using machine learning to improve eye typing with a system called Welfare eye typing. The last strand that my research group is exploring is what I call interaction science. So we, for instance, experimentally investigated a user's sense of agency. So agency is this innate feeling that an action is actually caused by your, an event is caused by your actions. And you can actually experimentally measure this sense of agency. And it turns out users' innate sense of agency is actually different if you're interacting, for instance, with a touchscreen compared to if you're interacting with your own skin, your own body. And we've done some research on memorability of gestures, some work on proxemics and attention-aware interfaces that track users' attention and adapt the information visualization display according to users' attention. And finally, we've done some interesting work, but unfortunately it's a bit out of the scope of this workshop, on modeling users' perception of their own performance. As it turns out, we're optimizing, let's say, a touchscreen UI, like a mobile touchscreen UI. We can shift around the sizes of the buttons. You can change the location of the buttons. But does this actually matter? And it turns out, even if you can find an objective performance differential, users are unlikely to discover that performance differential. They are unlikely to notice it. And this can actually be predicted very nicely using a logistic function with just 2 parameters. You can ask me about that later if you're interested in that. So, lots of stuff, but what they all have in common is that it's about designing intelligent interactive systems. So these are systems that infer or predict users' actions, typically using sensor data and machine learning. And I'm going to become much more concrete now and talk about some of the things I've been doing throughout the years. And in particular here, I'm going to focus on efficient and flexible communication methods. So, writing is a fundamental activity in human civilization. I think we can all agree. And actually, people have been thinking about how to design efficient text-enter systems for a very long time. One particular system I like to talk about is known as Ars Notaria, invented by John of Tilbury, a monk in medieval England. And what's interesting about this system is not that it's particularly clever, it's because we know the design process. It's actually documented. So in this system, letters are simplified to line marks, and common word stems are compressed into a series of line marks and dots. And how do you identify these common word stems? Well, you do frequency analysis. So at the time, they were very much into copying Bibles. So he did frequency analysis on the book of Psalms. So what does this tell us? Well, to make an efficient text-enter system, you need to optimize the speed by minimizing users' articulation effort. And you need to exploit redundancies in natural language using frequency analysis, which then leads to a probability model, which is now called a statistical language model. So both of these principles have been known for a very, very long time. And really what we're doing now is basically refining these principles and making them more rigorous mathematically. Okay. Now I'm going to talk a little bit about my small claim to fame, the gesture keyword. It's something that some of you actually might know about. So the gesture keyboard is a great example of how to apply these two design principles. So we did this work in 2001 in the beginning, but it took about 8 years before it hit the mainstream. So basically, how does a gesture keyboard work? Well, we've written some text, just then, comma, they're white. Let's say we want to write rabbit. So typically you hit the R key, you hit the A key, you hit the B key twice, then you hit the I key, and then you hit the T key. Which is a bit silly, right? Because we're not ever using innate dexterity, right? The dexterity of people in their fingers and hands. And we're also not utilizing any language information. If we're forcing people to basically hit the key, meticulously, precisely hit the key, go from key to key to spell out the word. So what a gesture keyboard does is to basically view this as a geometric representation instead. So R connects to A, which connects to B, we ignore double letters. Connects to I, connects to T. And this forms a shape. When the user gestures a shape, which may be similar, or which might be quite dissimilar, depending on the language model, the system figures out the intended word, which in this case is probably the word rabbit. So more mathematically, what we have is we have a prior probability estimation based on the previous set of words the users have written and the word under consideration. Let's say the word rabbit out of basically probably 100,000 words that we're considering. And then we have a likelihood model, which basically tells us how close this gesture is, how similar this gesture is to an ideal representation of the gesture in the system's memory. And there are many ways to do this. If you attend the workshop, I'll actually tell you about a few ways to do this, which generalizes beyond keyboards, by the way. But the important thing, which I think is intriguing, is that this basically forms a writing system in disguise, right? So we start with a QWERTY keyboard representation, but if you just look at the symbols, you'll find that it almost becomes like a shorthand symbol system, right? So these are the shapes for and Finland. Right? So they might be complicated, but actually after about 15 repetitions, they build up in user's motor memory. And once they build up in a user's motor memory, you can quickly recall the gesture directly from motor memory without using any visual attention. And this is what makes the gesture keyboard fast. So a traditional keyboard is closed-loop interaction. It's visually guided closed-loop interaction. You need to know where your finger is in relation to the intended key. With a gesture keyboard, it's always direct recall from motor memory, if you have learned the gesture. However, the beauty of this system is that actually, when you do this, while you're using a gesture keyboard, you are gradually becoming an expert in disguise. Because every time you do a repetition on the keyboard and spelling out the word by going from key to key, you are gradually building up the motor representation of that gesture. And does it work? Actually, it works quite well. And interestingly, it's no better than a state-of-the-art error-correcting touchscreen keyboard in the lab, actually. If you do a lab setting and you sit people down and give people a phone, what we're going to do is we're going to type both fonts on an error-correcting touchscreen keyboard, and they're going to be about as fast as a gesture keyboard. However, what is really interesting is that if you go out in the wild and you actually check what people are doing outside a lab, what they're doing is they're using their phone in one hand, and then they're swiping using a gesture keyboard with a phone. And this is much faster than typing on a... This is actually turns out to be faster and more reliable than typing with both thumbs, which, by the way, people don't do in practice. People tend to type with a single finger in practice if you actually observe a set of users. So, basically the point is not to beat the QWERTY here, the point is to keep the QWERTY, but just make it slightly better. And people have an option, you can type if you want. If you're tired of typing, you can gesture. And how do you learn how to gesture? Well, you just gesture from key to key, which is basically the same as typing from key to key. And if you do it a couple of times, you're going to be an expert in disguise. And if you do it a lot, you're going to be a real expert, you're going to be faster. So that's the point. The first version was released in 2004 for tablet PC. It was Java-based. It was in the press for a while. Then we started a company in 2008. This is me when I was young and beautiful in Beijing. And then we released it on iPhone and had between 1 and 2 million downloads. I don't quite depends on how you count, if you count updates or not. Got into time, etc. It was acquired by Newman's. And basically, now it's basically part of the Android operating system by default, and also actually, as of late, the Windows mobile system. And I venture to say that it's the only significant mobile text entry method that has achieved mainstream success in the last 20 years. And some extra things. So, based on this, there is a natural question: how do we design successful text entry methods? So I'd like to ask the question: well, how have we designed successful text entry methods in the past? There's been basically 5 successful mobile text entry methods in the past. We have the graffiti system, multi-type and predictive text, which some of you might remember. touchscreen keyboards, gesture keyboards, and physical thumb keyboards. And there are about 23 different design dimensions of mobile text print if you survey them all, which I have done. And if you look at the hundreds of text print methods that have been proposed in the patent and research literature, and you compare those design, how they fare against these design dimensions with the 5 mainstream mobile text printing methods, what you find is that the successful mainstream mobile text printing methods that have achieved widespread user adoption share 2 traits, okay, but are not shared among other unsuccessful text printing methods. Number 1, they have a high effective entry rate, right? So they're fast at an acceptable low error rate, because obviously entry rates and error rates are tightly interlinked. So what that means, they're among the fastest of their generation. And the second trait, which I think is more interesting, is they also exhibit very high familiarity for users, which translate into immediate efficacy, which means within the first minute of use, people already know how to use it, and they're already efficient at using this text entry method. So this is a bit of a problem, actually, because this suggests that basically we can do nothing, right? We're pretty much stuck where we are, right? And we can only do some sort of incremental steps, maybe with the exception of the gesture keyboard stuff, which I still would say is quite incremental. We're still using a QWERTY keyboard. We're just changing the mode of interaction. So we have these design constraints, a high effective entry rate, and high familiarity. So how do we go beyond the state of the art? Well, I venture to say that if we believe in a future of ubiquitous computing and wearable computing, etc., we also want to provide users with flexibility, right? So if people want to write in a particular style, we should be able to do so. If people want to correct text in a particular way, we should be able to do so. And also multimodality. So if you want to intermix, let's say, speech recognition, which has obvious privacy problems for one thing, with touchscreen interaction, which doesn't have privacy problems, but which is going to be slower. We can speak faster than we can use a touchscreen. Then you should be able to do so, but the trick is to do it in a seamless and flexible way. And finally, context awareness. So we have much better on-device sensors nowadays, and by using these sensors, we can improve the predictions that the models are making. And I'll give you one example to show you I'm not just waffling about something we have done, which is basically in this space, intersecting flexibility and multimodality. And it's called asynchronous multimodal text entry using speech and gesture keyboard. So we use a gesture keyboard, and we're also going to use speech. And the way it works is as follows. So you use a speech recognition system, you're going to have an experience like this. So the user says the cat sat. The system outputs the bat sat, because speech recognition isn't perfect, but it's getting a lot better, and it's never going to be perfect. The user then tries to correct the error using speech and says select bat. So this is a speech command. And the system recognizes this and outputs the bat sat dissect rat. And then the user gives up on speech recognition. So using our wonderful, fantastic system that never does anything wrong, the user speaks the cat sat. The system might still output the bat sat, but speech recognition isn't perfect. Then the user can gesture the word cat, or the user can gesture the word the cat, or the user can gesture the word cat sat, or the user can gesture the cat sat, or the user can speak any of these combinations. It doesn't matter. Or the user can type any of these combinations. It doesn't matter. And the system will automatically identify the error location, swap out the error for the correct word or set of words. And it actually works sometimes. So hopefully the system outputs the cat set. So the system automatically identifies whether the text should be either revised or corrected. And the way it works is that we have one modality, let's say a gesture keyboard, and we have time step 1 and time step 2. So we're going to guess a word between time step 1 and time step 2. So we might guess verb, we might guess the word V, we might guess the word free. Typically a vocabulary has 100,000 words, so that would be 100,000 word hypothesis at least, right? Then we might also have an epsilon transition, and that means actually for this time step we don't believe in a word, right? It was just a mistake, so we're not going to generate any word and move to the next time step. Okay, so this is called a word confusion, by the way. And what you can do is you can concatenate these. So these form word hypotheses of what the user is intended to write or speak, whatever. So if we have 2 modalities, we have 2 word confusion networks. One can be from a speech recognizer, one can be from a gesture keyboard. Or both can be from a speech recognizer, it doesn't matter, the system doesn't really care. The only important thing is that we have these word confusion networks and we have these probabilities assigned to the word hypothesis. So what we then do is we steal some of the probability mass from each word confusion cluster, and we're going to introduce wildcard transitions. So the wildcard transition means go to the next time step and generate any word. Okay? So that means we can insert words in the final word hypothesis. And we introduce epsilon transition, which microprogram means go to the next time step but don't generate any word. And And we insert these softened transitions, these transitions that soften the word confusion networks along both of the networks. Now, what we're doing, we also have another wildcard transition, which basically will stay in the same time step but generate any word. So this means we can insert an arbitrary number of words at any time step. Now, the name of the game is to search. So you might realize that this is actually a pretty big search space. It's huge. But the good news is that there is a very good model called a token passing model, which can find the highest joint probability of throughout both networks at the same time. So what we do is we have tokens, so these are magic tokens. Each token occupies a position in both of these networks simultaneously. And we're going to spawn a lot of these tokens. And we're going to explore different paths throughout these networks. And the nice thing is this can be completely parallelized, so the more cores the device has, the better it is. So a token is basically a very simple data structure. It knows the position of the token in both of the networks. It has an accumulated log probability. So a log probability is just a log transform probability, and the only reason you do it is because of numerical accuracy, so there's nothing special with it. And it has a previous few words of language model context, basically what we have built up so far. So what we do is we compute the cross product of all possible token roots for an individual token. And then what we do, we only consider a move valid if it obeys two rules, okay? So at least one of the tokens, one of the moves, right, through one of these two networks must generate a real word, okay? We are not both allowed to generate a wildcard word. So what does that mean? And then we need a real word to present to the user. And multiple word confusion networks, right, such as these two, if you go through them at the same, for a particular move, if they both generate real words, these words must match. Because you can't speak two words at the same time, right? So very simple rules. So does this work? So you have a lot of hyperparameters here. You have basically all the epsilon transitions and all the wildcard transitions, and all of these are weights that you can do, parameters that you can tune. So what you do is you collect a lot of training data, and then you do something called grid search, which is a very hacky method but very efficient method. The only way to really train a model with these many hyperparameters. And you train it on lots of amount of training data. And then what you do is you can do experiments. So does this actually work? Well, we had people using a touchscreen keyboard. So they were walking around in the physics department in Cambridge at the time. And they were using either a gesture keyboard or continuous speech recognition. So we were prompting them sentences, and we're telling them to basically input whole sentences, either by speech or by touch, using a standard, using a gesture keyboard. So the first thing we tried was to fuse entire sentences. So here we are fusing a speech recognition sentence and a gesture keyboard sentence. So what you can see on the left is the word error rate for speech recognition alone, which is 27%, which is pretty much a disaster. And gesture keyboard, for gesture keyboard, the word error rate is 40%, which seems high, but believe me, if you do realistic experiments with people walking around indoors and outdoors, etc., using a mobile device, you're going to see high error rates. If you merge both of these modalities using this model I just showed you, the word error rate decreases to 6%. You can also do this for search queries. So search queries are more difficult than sentences because there's less context. A typical search query will consist of 1 or 2 words. And if you do this, similarly, if you merge the two together, you see a substantial reduction in word error rate. What you can also do is you can have an erroneous speech recognition result. Let's say that's what we investigated in this experiment. And then you can identify an error in the speech recognition result that you want to correct by gesture alone. So we find sentences that have at least one speech recognition error. And then we find a corresponding gesture keyboard input, which might be correct, which might be even wrong. And then we fuse both of the networks together. And if you do this, you can find that the word error rate goes down from 48.5 to 28.8%. So a substantial word error rate reduction, which is pretty amazing if you think about it, because the system has no knowledge of even if there was an error to begin with, and it doesn't. And if there was an error, the system doesn't have any knowledge of the particular error location there. All right. So that's about merging. Now I have a few minutes, so I'm going to do something which I think is a little bit hotter these days. Smartwatches, which everybody seems to be talking about. I don't particularly believe in a smartwatch because I don't wear a watch, but felt I should do something anyway. So I'm basically going to tackle the problem of typing on a smartwatch. So going back beyond the state of the art, we now know how to build a successful text-entry method. So how do we build a successful text-entry method? Well, we should obey these design constraints. right? High effective entry rate and high familiarity. So what does this suggest when it comes to typing on a smartwatch? Any ideas? Anybody has an idea? Alright, I'm going to give you one idea for free. It's called sentence-based decoding, which is a fancy word for something which is very, very simple. You take the regular touchscreen keyboard and you just make it very, very small, 25 millimeters wide or 40 millimeters wide. And then you tell users, just do what you already been doing with your iPhone or Android phone or whatever. Just type the keys as fast as you can. And we'll figure out what you want to type. Now, the nice thing with that idea is A, it's going to be fast. And B, it's very, very similar to what people are already used to. So that's the whole point of this system. How do we best design such a system? Well, we have tabs and we want to convert them into text. So we have a noisy tab sequence, such as this one. What is the user by? You can play decoder. Alright? So the user is probably trying to say, have a good day. And output probabilities, so we compute the probability of the letters given the tabs, which is proportional to combining a touch model to a language model. So what's a touch model? Well, in this case, it's a very, very simple touch model. It's just a two-dimensional Gaussian distribution set on each key. It can be tuned in X and Y dimensions specifically for each key. And basically, whenever we have a touch point, we sample the two-dimensional Gaussians for every key. And that gives us a likelihood of the user intending a particular key. So, for instance, for the letter, if you're investigating the likelihood of the letter Q, and I'm hitting the key, the N key, which is very far away, there will be a very, very, very small likelihood that actually I hit the Q key, right? Because a two-dimensional Gaussian distribution is infinite, right, in the text. So there will be a likelihood, but the likelihood will be very, very small. But if I hit the Q key, bang on the center, there's going to be a very, very high likelihood that I intend to hit the Q key. A language model basically assigns probabilities to word sequences. And what we use here is Twitter, because Twitter turns out to be useful for something. It's very useful for predicting mobile text. So we have a laptop in our basement at the physics department that we've collected Twitter data for 5 years now. So we use that model to train a language model, which is very good at predicting mobile text. Then we do the decoding step. So we have an observation sequence. Let's say 3 tabs, and we want to decode these 3 tabs. So what could a user be writing here? Well, the user is hitting something close to the F key, to the O key, and to the D key. So we're going to start with a token again. So we're going to use token passing, as I talked about earlier. And this token is going to spawn a token for observation 1, and it's going to guess the letter F. It's also going to spawn tokens for any other hypothesis of this particular, for this particular observation. So it's going to spawn a hypothesis for every letter on the keyboard. And it's also going to spawn a hypothesis that actually the user didn't intend to hit a key at this observation, for this observation 1. So we're going to spawn an epsilon transition, which means go to the next step and do not generate a letter. It's also going to spawn tokens for the same observation, meaning that actually this tab was actually intended to be multiple letters, and so on and so forth. And then the tokens in observation 2 are going to have a similar process, and they can also spawn tokens that stay in observation 2, etc., etc. And in the end, some of these tokens are going to end up having no observations to deal with. So they carry the hypothesis of the users. So one hypothesis very probably likely is going to be the word God. Another hypothesis might be the word go. And if we let the system show on long enough and search for different solutions, it's probably also going to guess the word good. So G or D. So it stayed in one observation and generated an additional letter. This search space is actually infinite. So it will never terminate. So the way to keep this trackable is to use what's known as beam pruning. So what we do is we only explore token hypotheses that have a certain probability over a certain threshold. And this threshold is adapted. So what's typically done in practice is that we have one core token where it's going through the entire sequence at first. And that token is going to have a best probability for every observation. And any token we spawn for a particular observation has a probability less than a certain threshold compared to that best probability we currently have. And then we update that best current probability as we are decoding. So this can be nicely parallelized, and it's very good for multiple devices. Big question is, does it work? Well, we did a bunch of experiments. I don't want to bore you too much about these experiments. One was visual feedback. We were interested in if we don't output any letter feedback when the user is typing, will the user actually type a bit faster? We're basically encouraging people to not worry about intermediate feedback. Just type out an entire sentence as quickly as possible. Turns out that doesn't really work. It doesn't really matter, so we're just going to skip that. And the other point here is to annoy my PhD supervisor who works at Google Mountain View in the Android keyboard team. We basically beat the Google keyboard in the error rate there quite substantially. It's statistically significant and everything, so that's nice. The second thing we investigated is word delimiter actions. How do you actually space out words? Maybe you shouldn't let users press space at all. People should just type, go from letter to letter, just ignore spaces altogether. Or maybe people should be provided an opportunity to type space. Or maybe people should be able to use a novel action such as swiping to the right, which is a great signal for the decoder. Right? It's a very certain signal that the user intends to separate a word. Turns out it actually doesn't really matter. The no space alternative was actually quite bad here, but once you retrain it on enough training data, because we didn't have enough training data, it actually results in a very low error rate. So in a final system, what we're actually doing is we're letting people separate words however they want. So people can hit the space key, they can swipe from left to right, we can ignore it altogether and just go from letter to letter and skip spaces altogether. It doesn't matter, the error rate is the same. Finally, we did this smartwatch thing. Smartwatches seem to be an obsession nowadays. So we tested basically 3 screen sizes. We have normal, small, and tiny. And they get progressively smaller. And these are the results. Basically, you can type at 40 words per minute on a smartwatch keyboard. So a 25 millimeter keyboard, just fine. The error rate is a bit, the character error rate is a bit high on the tiny one, the 25 millimeter one. Actually, if you let users train more, right? So this was quite a small experiment. The error rate actually goes down to below 5% character error rate, which is typically judged as the acceptable error rate level. Remember, when you're using an text entry method, there are always going to be errors. Errors are inevitable. The backspace key is actually the most frequently used in a standard keyboard. So basically, for typing on a smartwatch, you don't really have to do much. You just have to make the keyboard really, really small, and then use a clever decoding algorithm to figure out what the user is typing. And that's it. And do I have a more time? No, probably not. Okay, thank you very much.
Right, we have time for a couple of questions. Please, Matt.
Actually, I have 2 questions. First, have you tried any personalization for this model? So not only the language model, but also user history. Or how to predict what the user wants to say. Maybe you're remotely using person. And second question about smartwatches. Battery sizes are quite limited in battery in small devices. So have you have any idea about how energy efficient is typing and running?
Yeah. For the first question, actually, we are not as original as we think we are. I mean, the typical users active vocabulary. 5,000 words. So adaptation works, basically personalization works. And the way to do it is to use an adaptive language. So you simply update the probabilities forward to take it from the typical user. If you can mind users send email, that's the best source. Typically there are practical problems in doing this. But it's definitely works. It's not adaptive language, it's a very common technique. When it comes to touch models, what you should do is, well, first of all, this model is adaptive, right? Because it's trained in 2-dimensional Gaussian in the X and Y direction for the individual keys, and you can do that tailored for each individual user. But what we really should do is something we did in a previous paper. We used Gaussian regression as a Gaussian processes. So if you use Gaussian processes regression, right, it will actually learn these touch distributions very nicely as you go on. That's a very simple technique to implement. The reason we didn't do it here is because, frankly, it doesn't make a difference. The secret sauce when it comes to this whole text entry decoding methods is the quality of the language model. And our mobile language model is just very, very, very good. So any marginal improvement in the language model doesn't make a dent. We basically just need a noisy signal from the touch model. As for your second question, actually the best way to do this is to rename the server. So it actually it feels instantaneous, and so that solves the energy efficiency problems. Otherwise, yes, if you're decoding, it depends on the beam width, but the narrower you make the beam, the more greedy the algorithm is, and the less energy you